Hello everybody, this is a lecture to accompany the Uncertainty module. I will be presenting an overview of issues related to spatial data uncertainty that should support the readings from the big book of GIS that are linked to on Canvas. Some of what I'm presenting today will be taken directly from some very articulate sources on the subject of data quality, and I will provide all those sources and references on the Canvas Week 6 overview page. So I want to make the point that until really recently, people involved in GIS work, both developers and users, have paid very little attention to the problems caused by uncertainty of spatial data. The power of GIS really comes from being able to collate and cross-reference many types of data by location. Unfortunately, every time we add a new data set to GIS, the GIS inherits all of the errors, both known and unknown, of the data. And this can lead quickly to error propagation and various cascading effects of uncertainty, which in turn can lead to undefined margins of error on our results that are rarely addressed or even, understood. So the key point that I really want to get across today is that even though error is a pervasive component to all GIS analysis, there are ways to keep error to a minimum through careful planning, and there are methods for estimating its effects on your GIS outcomes. Awareness of data uncertainty should make us all very sensitive to potential limitations of our GIS solutions, and that's really the point of this, awareness. So that's where we're going to start. Okay, this is a great historic map of Paris, and it just goes to illustrate that we have to make choices when we're mapping. When we're collecting data, when we're presenting data, we can't map it all. It is pretty clear that even in a situation like this, where we're just marking street names and basic places, we haven't even added complex layers of data, it just becomes a cluttered mess. The world is infinitely complex, and we have to limit what we're going to capture, right? If we mapped everything at its full resolution, we'd have a map that's the same size as the world, and that would be stupid. We have to make choices about what to collect, and every simplification leads to loss of information. Uncertainty is inevitable. There is no such thing as a perfect GIS data, right? It all has error of some sort because we generalize. We have to. The first step in dealing with error is being aware of it and understanding the limitations of the data that we're using. Okay, so when we talk about data quality, what exactly are we talking about? Uncertainty is one of the first terms that I want to address. Uncertainty is sort of an amorphous concept. It's a discrepancy between reality and its representation. So it's kind of a softer term. When we talk about error, we're talking about the actual measurement of uncertainty. So error involves assessing both the imprecision of data and its inaccuracies. We can also talk about, here we go. Here's an example where we have a location. We have a quantified amount of error on our location. That leads to a range of uncertainty. I hope that makes sense. The uncertainty, we don't know what direction the error is. We just know that for example, we know that this location is going to be within 5 meters of its true location. Well, if this is a 5-meter line, we have now this large area because we don't know which direction the error is in. So we also can have bias in our data, and that's different than a random error. So for example, you're tasked with digitizing the center line of the Mississippi River, and there can be random errors where you maybe just physiologically can't stay on the center line. Maybe there's a temporal error where we pick up this oxbow lake. Maybe it used to be a part of the main channel, now we just have outdated data. But these are kind of random or non-systematic errors. But if we were to have a datum shift where there is a systematic distortion of this data and an error that propagates all throughout, that's called bias. And then just to be very specific about accuracy and precision, in order to really understand the relevance of these terms, we need to kind of define the difference between them. So accuracy can be defined as the degree or closeness to which the information on a map matches the values in the real world. That's kind of what we talked about in that last slide. When we refer to accuracy, we're talking about quality of data and about the number of errors contained in a data set. Spatial data accuracy can refer to both geographic position and attribute or conceptual accuracy. So it not only has to do with the location, but the attributes of the data. Precision is different. Precision is how detailed the measurements are, or how exact the description of data is. So how detailed are the attributes that are being collected, or how much precision, how exact is the measurement that we're making. So precise data can be inaccurate, and accurate data can be imprecise. That's the other thing to keep in mind. This image demonstrates the difference between precision versus accuracy, increasing accuracy, increasing precision. So figure A here, well, it's important to know that the bullseye of each target represents the true value of the entity that's being measured, and the red dots are the measured value. That's kind of how these are set up. Image A is precise and accurate. Image B is precise but inaccurate. This is the true value. Image B is precise, image C here is accurate but imprecise, and then D is just neither accurate or precise. So hopefully that makes some sense. Understanding both accuracy and precision is really important for assessing the usability of a GIS data set. And it's good to know too that sometimes inaccuracy can be corrected. All right, so types of map accuracy. The obvious things, the ones that are easy to spot, are age and scale. Some of the types of data accuracy or map accuracy that are a little bit harder to spot are data format, so whether we're choosing to store our data in raster vector format, positional, attribute, and this especially if there's a little bit of bias in there, attribute and conceptual accuracy. The first one I just want to talk about is temporal accuracy. So a map is a representation of real-world objects at a given point in time. And the reliability of a data set typically is going to go down as it gets older. And this is especially true of data that would frequently change, such as urban housing or ice caps, right? And you guys just spent a lot of time with Antarctic data and data from Antarctica. And obviously you were working with an older data set, and certainly these values have changed, right? Even the coastline has probably changed as glaciers calve. So yeah, temporal accuracy is really important, and it highlights the importance of metadata, which we're going to talk about in a few minutes. Metadata is the supporting documentation that describes spatial data. Hopefully you're aware of that by now. But yeah, it's just important to know that a lot of GIS projects can be so big that they can take years to complete, and it's often very possible that the earlier data collected is out of date by the end of the project, for better or for worse. It's just good to know. And then scale. So scale is something that is definitely related to accuracy and precision. Here's a map where we've got rivers that are mapped at a scale of 1 to 100,000, and rivers that were mapped at a scale of 1 to 24,000, which is the typical, topo map scale. In general, larger scale maps show more detail than smaller scale maps, and larger scale maps also tend to have greater accuracy than smaller scale maps. This is really challenging with digital data because data is going to be created at a specific scale, but once it's loaded into GIS, it was created with specific levels of accuracy and precision, but when you throw it in GIS, it's so easy to zoom in and out and kind of take it out of its own context. And it's important to know that data is created to be used appropriately at specific scales and in combination of data with similar scales. And you need to make sure that you're using your lowest common denominator when you're reporting your final results. The lowest common denominator of scale and accuracy and resolution needs to drive the precision with which you report your results. So GIS is going to process your data whether or not it's appropriate to do it, right? And it'll often give you like 8 decimal places, even if you're working with really coarse data, and that's where it's up to you to understand and think about these things going in so that your results are in agreement with the inputs. All right, data formatting. This is another kind of hopefully relatively obvious way to control accuracy, but the way we choose to represent the data can impact accuracy. So whether we choose to represent data in a discrete fashion or continuous can have a lot of implications. When we convert from raster to vector data or from vector to raster data, we can end up with inaccuracies. And this can perpetuate and propagate because you maybe have a raster data set that was originally interpolated from contours. And then you take that raster data and create contours again. Well, each time you do that, you're having a cascading effect of error. So it's important, again, to know the lineage of your data. You don't have any way of knowing how many times that's happened over the course of time. Things can be dropped, connections can be made when we're making those kind of vector raster conversions. Coordinate system transformations can slowly erode away the quality of your data. So if you've got data that was projected, and maybe somebody transformed it to a geographic coordinate system and changed the datum, and then you get your hands on it and you transform it to a new datum, every time that happens, we're slowly eroding away at the initial quality of the data. And as you know from that Greenland lab where we had you measuring, just flat out the coordinate system that you're in can have such a drastic difference, make a drastic difference on the measurements that you're making. All right, I'm going to stop there and we'll pick up in the next section.